Please, Mr. Piazzoli, you can start your presentation.
Thank you very much. Good morning, everybody. The study I'm going to present shows our knowledge-based approach, consisting in the use of some data mining statistical techniques, can be applied for the planning of the proper treatment trains in a drinking water supply system. And in particular, the real case study of the Milan city in Italy was considered. Let's start with a brief introduction to the case study, to the study case. And Milan is located in the north of Italy, in one of the most densely populated and industrialized area of Europe, has a drinking water demand higher than 200 millions of cubic meter per year that is totally complied by groundwater. This water is captured by more than 500 wells spread in all the city area, pumping water from the second and the third aquifers from a variable depth. And water is then collected and treated in 27 drinking water supply units, each one supplied by a variable number of wells, from 12 to 24. And the aim of this study was to plan the proper sequence of treatment in each treatment unit of the system. And this operation is usually approached by two steps. The first is the determination of the constituents of the compounds to be removed or controlled. That is based on the knowledge of the source water quality and the regulation limits. And the second step is the selection of the proper treatment train, and often is based on the comparison of different alternatives. And the performances of these alternatives can be strongly case-specific. They can depend on the water composition. So very often the experimental evaluation of these processes is required. And in a situation like this case study, there can be some critical aspects. In particular, we have a high number of wells capturing water from different points, and different pollution plumes are intercepted, so the knowledge of the composition of the water and the contaminants to be removed can be quite hard. And secondly, a high number of units must be planned and designed, so a high number of experiments can be required in order to evaluate the performances of the treatments in each treatment unit. So in this work, data mining approach was applied in order to synthesize the available groundwater quality data and to reduce the number of experiments needed to assess the performances of the processes. This is the data set that was analyzed. It derived from the monitoring activity of the drinking water supply service of the Milan city, and it was composed by the values of 88 parameters determined on the different groundwater samples captured in all the urban area. And so this database was characterized by a high number of parameters with a quite complex spatial distribution. And moreover, for some of these parameters, values higher or very close to the Italian standards were found. And in particular, those reported in the slide that are nitrate, some groups of pesticides and volatile organic compounds, and chromium. So this database was analyzed by a data-driven approach consisting in a sequence of factor analysis and a cluster analysis. The factor analysis was applied as a dimension reduction tool in order to reduce the size of the original database. In fact, this tool allows to identify within a large data set groups of parameters strongly correlated, and considering them as a unique parameter that is called factor. Then the spatial distribution of these factors was evaluated by the cluster analysis with the aim of recognizing typical groundwater compositions in the capturing wells and then in the treatment units. So let's look at the main results. Factor analysis allowed to extract 16 relevant factors from the starting 88 parameters. And these factors explained almost about the 60% of the total variance of the data. So we were effectively able to reduce the size of the database without losing the information associated to the original database. Moreover, it could be noticed that the parameters most correlated to each factor were always related to a common source of pollution or shared very similar physicochemical or mobility characteristics. And some of these factors are reported in the slide. And for instance, I've marked factor number 3 and 4 that, as you can see, are all associated to pollutions by heavy metals, or factor 15 and 16 that correlated different kinds of pesticides. Then the cluster analysis was applied, and almost the totality of the data were grouped in 8 clusters on the basis of the factor scores. And it was possible to give an interpretation of these 8 clusters, looking at the parameters most correlated to each factor. And in particular, we can see that we have the cluster G in blue, that it's the most frequent one, grouping about 60% of the data, that showed the average factor scores, and so identified water characterized by average quality. Secondly, we have the cluster E, grouping the 50% of the data, with a couple of factors with scores slightly higher than the average, and associated to nitrate and pesticides high concentrations. Cluster H, with high concentrations of chromium, and all the other 5 clusters, indicated by the orange arrows, with one factor showing a very high factor scores, and associated to punctual and specific contaminations due to the presence of groups of 2 or 3 organic micropollutants. Finally, the distribution of these clusters in the 27 treatment units of the system was evaluated, and we can notice that there are basically 4 main kinds of treatment units in terms of groundwater composition. A first group where water totally comes from wells belonging to the cluster G, so with an average quality. Another group that are fed by water coming from a mix of cluster G and E. Another group with the further presence of the cluster H. And a last group with the units characterized by the presence of at least one of the other clusters, so affected by specific and punctual contaminations. So, thanks to the data mining techniques, we were able to identify the groundwater composition in each treatment unit of the area. On the basis of the regulation limits, the constituents to be removed were selected, were individuated, and possible treatment processes were selected and then experimentally tested. In the second part of the presentation, I'm going to show the main results of these experiments, but the most important point is that the data mining results were used to select the most representative groundwater samples to be tested during the experiments. And let's start with the evaluation of the biological denitrification process for the removal of nitrate that was tested on a groundwater sample coming from the unit 6 that it's reported in this slide. So the process was tested at pilot scale in the biofilter reported in the slide. You can see the main parameters of the experiments. And the biofilter was fed with groundwater coming from capturing wells, affected by the presence of nitrate, of course, and also by the presence of different kinds of organic micropollutants, some volatile organic compounds and some pesticides. In this slide, the main results of the experimentation are reported. The efficiency and the completeness of the denitrification process was evaluated as a function of the main operating and design parameters. And we found that satisfactory removal of nitrate and nitrite concentrations in the effluent below the Italian regulation limit were found for a carbon supply higher than the 90% of the stoichiometric demand, and for volumetric load values lower than 0.8 kilogram of nitrogen per cubic meter per liter. The average nitrate and nitrite concentrations observed during the experiments are reported for this carbon supply condition and as a function of the volumetric load. And it can be noticed that the nitrate and especially nitrite concentrations were obtained for the lowest volumetric load values, very close to the outlet of the biofilter. So we have found that denitrification was suitable for the removal of nitrate. However, in all the treatment units of the system, we have to remove also pesticides and volatile organic compounds. For this reason, we tested the performances of adsorption process, in particular on 3 groundwater samples, 2 coming from the units 8 and 11 that were selected as representative of an average and diffuse contamination, and on samples from unit 14 that are representative of a punctual and specific contamination due to the contribution of the cluster C in purple in the captured groundwater. The process was tested at laboratory scale by a series of experiments for the determination of equilibrium isotherms, and let's look at the main results. In the chart, the maximum removal efficiencies for the different groundwater samples are reported for all the organic pollutants initially present in the water. We can see that pesticides, despite the low concentration, were well removed in all the samples. Most part of the volatile organic compounds showed a quite low removal efficiency that was probably limited by the low initial concentration, and 3 volatile organic compounds that are also those regulated by the Italian drinking water standards were initially present at a significant concentration. Perchloroethylene that showed the highest removal efficiencies, trichloroethylene, and chloroform that showed the lowest affinity with the activated carbon. Another interesting aspect that was found with these experiments is reported in this slide that shows the equilibrium isotherms computed for PCE and TCE in the 3 groundwater samples. And it can be noticed that PCE is similarly removed in all the samples, despite the very different initial concentrations. On the contrary, TCE showed a very low removal efficiency in the samples from unit 14 in red, despite the initial concentration of TCE was comparable in all the samples. And the reason is probably the high concentration of PCE in that kind of groundwater, suggesting the occurrence of competition phenomena between these 2 compounds. And so these experiments showed that adsorption is a suitable process for the removal of these organic micropollutants. However, in presence of less adsorbable compounds as chloroform or competition phenomena as PCE and TCE, an upgrade of the process could be required. And among the different alternatives, we wanted to test the adoption of an aeration step before the adsorption phase. And the reason was that many units in the system were affected by high levels of volatile organic compounds. So the hair stripping was tested, in particular in a groundwater coming from the unit 12, was tested at pilot scale, and I just want to point out the very low air-to-water ratio, the very low airflow adopted during the experiment, since our goal was to partially remove the most volatile organic compounds during the aeration step in order to increase the lifetime of the carbon. And we found that the compounds initially present at relevant concentration were removed with significant efficiencies, also with these very low values of air-to-water ratio, confirming the suitability of this solution for the treatment of this kind of water. However, the proper design of such a layout, composed by an aeration step followed by an adsorption step, must be carefully designed, considering the costs associated to both the phases. And an example of this kind of assessment is reported in this slide. We evaluated the costs, the operating costs related to the air supply in the aeration phase and the substitution of the activated carbon in the adsorption phase, fixing the PCE concentration at the inlet, at the outlet, and varying the removal efficiency in the aeration phase. And we observed that significant decrease of total cost could be obtained already from removal efficiencies around 30% in the aeration phase. So let's look at the main conclusions. In this work, a knowledge-based approach was applied for the planning of the treatment trains of a drinking water supply system, in particular in the Milan city. Data mining techniques allowed to identify the main sources of contamination affecting the area and the typical water quality fed in each treatment unit. The most suitable processes were identified based on experimental results obtained on few and specific representative groundwater samples. And these results had a general validity and could be extended to the whole urban area. So the main conclusion remark is that data mining is an effective supporting tool to plan an efficient and sustainable water treatment system, coping with a complex groundwater quality. I would like to thank the other authors of this study and the staff of Metropolitana Milanese that manages the drinking water supply service of the Milan city. Thank you very much for your attention.